All right, I have the pleasure of introducing you to the following three Bell flight engineers and one of our very own Collier Aerospace engineers. First, I'd like to introduce Kerry Cross. Kerry's an engineering manager at Bell Flight focused on aerospace structural design and analysis. During his early career, his discipline was in structural dynamics, fatigue, and damage tolerance. He supported conceptual design through sustainment on both military and commercial programs such as the U.S. Army FireProd program, V-22, DARPA Sprint, and the Virgin Galactic Delta program. While most of his tenure was spent on the analysis side, he also has background in full-scale tests and flight tests. Kerry attended our HyperX Users Conference 2 years ago along with his colleague Amber Risa. Shortly afterwards, he brought our Collier team on to support the usage of HyperX on the Virgin Galactic Delta program. Kerry has been instrumental in the adoption of HyperX on both the program at Bell. His role ensured a programmatic implementation of the HyperX tool from both a top-down and a bottom-up approach. Next up is George DeLeon. George is a technical manager at Bell Flight, contributing to the Virgin Galactic program. George earned a bachelor's degree in aerospace engineering and engineering mechanics from the University of Texas in Austin and a master's degree in mechanical engineering from the University of Texas at Arlington. With over 19 years in the aerospace industry, George has gained significant experience, including 13 years in rotorcraft, 4 years in fixed-wing aircraft, and 2 years in space vehicles. He has experience in flight test correlation, fatigue analysis, in addition to general airframe stress analysis. George has played a crucial role in the technical implementation of the HyperX software on the Virgin Galactic Delta program. His diverse background provided crucial insight of how to best integrate HyperX into Bell's engineering workflows. His leadership and guidance of the team has been pivotal in the success story of HyperX usage on that program. And now I'd like to introduce Max Silva in the middle there. Max earned a master's and bachelor's of science degree in mechanical engineering from Brigham Young University. He has more than 22 years of experience performing stress analysis of primary and secondary structure for both commercial and military aircraft. Currently, he is a stress lead for the Virgin Galactic Delta program. Max has been effectively demonstrating the power of the HyperX software at Bell and plays a ground floor advocate role in adoption of the tool on the Delta program. In combination with his technical experience and savvy HyperX software skills, he has led his team by example and was fundamental in scoping out the analysis process in HyperX to support part release. And lastly, I'd like to introduce our very own Justin May. Justin is a senior aerospace structural engineer. Has been with Collier Aerospace for almost 4 years. He's in the project lead on our engineering services team, supporting this Bell team on the Virgin Galactic Delta program. I'd like to express our company's gratitude to these three Bell team members here today for being champions of our HyperX software at Bell Flight. Without further ado.
Thank you, Brent. And first of all, before I get going, thank you to a lot of the folks in this room, all the Collier engineering services support, all of the scripting folks, and sort of back-end folks as well. I know the program has been very aggressive on schedule and weight, and I know a lot of folks in this room worked nights and weekends to get us across the finish line, and we're not quite there yet, but we're close. So thank you to everyone for all the support over the last couple of years. So you're probably wondering what is this? Why is this vehicle on the screen? This is not a Virgin Galactic spaceship. This is a Bell X-1. It's a rocket ship. There was some restrictions on the images we could use from the OEM, Virgin Galactic in this case. So I chose a different rocket ship that I also like. So in many ways, this was the first level flight, I'll call it rocket ship, to break the sound barrier with the pilot Chuck Yeager. In many ways, this program was the first, first of its kind as well. So several firsts throughout the program. So the first program at Bell to deploy HyperX at scale, meaning not just using it for conceptual early preliminary trades, but using it all the way through preliminary design and part release, as well as we will be using it for MRB support and build support. The Virgin Galactic Delta class spaceship is we'll get into in a little bit in the next few slides, but it's the mission or the vision of Virgin Galactic is to bring space flight to the masses. So that's another first that's we're trying to accomplish on this program. So another piece of this history a little bit that's been on our minds as we've gone through this development effort is that Bell later went on after this to design the Apollo lunar lander training module. So we were part of the Apollo mission, and we reference back to those times and sort of celebrate our achievements. And on this program, we had T-shirts made that had the Bell logo and the Virgin Galactic logo, and they say "Return to Space" in huge letters. So it's cool to get to work at Bell. My family's all from DFW area, and I know some of these folks are as well. So rotorcraft are awesome. There's never there's plenty to learn, and you can spend your entire career learning. But I think every kid wants to work on a rocket ship someday. So I love the program, and that I get to work on something really cool other than rotorcraft, and I don't have to sell my soul to Elon. So all right, so what I'll talk about a little bit today, I'm going to go through the mission and the vision, and then the who's doing what in terms of Bell versus Virgin Galactic, and then some of their other suppliers. And then I'll go through the design changes from Unity, their prototype spaceship, to their Delta, which is their production spaceship. And then I'll kind of weave in throughout the topics, how Collier and HyperX tool were involved in, and continue to be involved and help and also help us be successful. Okay, so just a little bit of background about the spaceship itself and the mission and the vision. So this is the prototype. This is the Unity spaceship. Some of us got to go fly out there to New Mexico to watch it perform. I think it was Unity flight number 5. So what happens is they're sort of in a remote desert area. It's an FAA sanctioned airspace for them to complete their mission. There's not a lot of other air traffic in the area, as you can imagine, so it's at a spaceport. This spaceship takes off from a conventional runway mounted to a mothership. I think we've seen some of the other pictures of the mothership and Yvonne's presentation yesterday. But it takes off mounted to the belly of the mothership from a conventional runway, turbofan powered engines, and it climbs to an altitude of 50,000 feet, where it undergoes a cold soak, roughly minus 112 Fahrenheit, which is important for the analysis side of things. And then it's dropped. The mothership releases it, and it undergoes a momentary free fall until its rocket engines ignite, and it gains speed to about a speed of Mach 3. And it undergoes a sort of parabolic flight path where it eventually gets into a vertical climb, and the passengers experience about 3 Gs down and 5 Gs aft force. So it's a pretty impactful phase of the mission there. So then it climbs up to our ship will climb up to the Kármán line. So which is, it's important for the astronauts, the participants, to be able to say that they've gone past the Kármán line and that they're officially astronauts. At which point the feather system, which is what Bell is designing, and I'll get into in a minute, this sort of the tail end, the booms and the flap, they fold up, and then through conservation of angular momentum, the spaceship performs a backflip, and you can kind of see the windows in the top of the cabin and the fuselage there. So the passengers then unbuckle their seatbelts and they float about the cabin, experiencing weightlessness for 5 to 10 minutes or so. And so they get to look out of these windows on the top of the cabin, down at the Earth. They get to experience the overview effect, which is described as a euphoric feeling and a feeling of deep connection back to the Earth and the people on the Earth. So this is the sort of the feeling that that Virgin Galactic is trying to make available to more and more people. They want it to be as inexpensive and accessible as commercial air travel is now. So at one point, only the ultra wealthy could afford to fly on a commercial airliner, and now anyone can get in their bunny slippers and sweatpants and go get on a flight for $100. So that's kind of what they're trying to do. They're trying to make it accessible to the masses. This is the next step on the journey, and they feel that it's an important mission for folks to get to experience this and bring their learnings back to Earth and their loved ones. So. So after the the backflip and the weightlessness, the participants have to return to their seat and buckle their seat belts. The backflip maneuver completes. The feather system is still feathered up 60 degrees, and so it returns. The spaceship starts to return into the thinner parts of the atmosphere as a reentry vehicle with its belly down. There is where it experiences roughly a 350 degree Fahrenheit OML temperature, and so then it kind of the boom sort of guide it down as it re-enters the atmosphere, and then as it enters the thicker parts of the atmosphere, the feather folds back down, and it becomes a glider, and it's unpowered the whole return flight to Earth, and it glides down to the same runway that it took off from. Okay, so a little bit about the Bell content. So Bell designed and is building the feather system, which is shown on the screen here. We used BMI skins and BMI substructure. BMI enabled it's a high temperature resin system it's good, better to higher temperatures and retains its strength to higher temperatures than a traditional carbon epoxy system. What it enabled Virgin Galactic to do is remove a lot of the thermal protection system that they had in place on their prototype ships. So their thermal protection system previously was painted on or applied at a very sort of in an imprecise way, and they had to sand it down to OML, and it would sometimes crack, and it was a huge maintenance burden. And so their goal with the Delta program was to get rid of all that thermal protection system. It's a huge weight benefit. They switched to BMI instead of carbon epoxy material system that they had previously, and that was sort of the play there to improve the maintainability and the takt time and all that stuff. So we used metallic substructure and BMI substructure, metallic at the complex loaded joints, the big joints. We had to design for manufacturability, producibility, so they were big on takt time and turn time, so they wanted to be able to go from producing one spaceship per year, which is kind of the rate they could do before, to 3 spaceships per year. So we had to configure the joints in a manner that enabled that. We also had to configure the joints for logistics, right? Because previously Virgin Galactic had built all of these in Mojave, in their Mojave facility, and it was all hand laid up, and they had bonded joints, and they could build it up in one piece. But now we had to, with their other suppliers, supplying the fuselage and the wing, and then us supplying the feather, we had to be able to ship it to different parts of the country, and we had to, this is roughly for dimensions, the booms are 30 feet long and 9 feet wide, and then the span of the wing is about, I want to say 30 feet or so. So we had to find ways to, ship this around the country, and our our design reflects it, right? So we had to make tough decisions on joints and where we were going to break the structure up and all that stuff. So the other big KPP that was important, that is important to Virgin Galactic, is the turn time. So again, going back to the TPS, getting rid of the TPS improves the turn time. This is, decreasing the amount of time between flights so they can get more revenue generating flights each week. And so I talked about TPS a little bit. I talked about how our joints were configured for logistics and for where the thing is built. But then we also had to consider inspectability. So transitioning from a fully bonded joints to bolted joints, we had to consider what joints could be inspected and should be inspected and all that stuff. So that definitely went into some of our design decisions. Minimizing the number of inspections was important to VG. So let's see. That's all on this slide. Okay, so who was doing what? I talked a little bit about it. So Virgin Galactic is the design authority. They're the OEM. They have to sign off. Ultimately, they have a chief engineer, project engineer signature on all of our releases. So they're the ultimate decision makers. They keep the ship level mass properties. They take care of the flight sciences, mechanical systems. But Bell is the detailed design, the engineering design. We do the structural analysis. We do our own accounting of the mass properties. We do a BFEM. We maintain our own BFEM, and we do the maintenance of that. But then, so where does Collier come in? So I'll talk a little bit more about it later. But the Collier team's role in this was really around. They were a supplement to the engineering analysis stress team. So they performed analysis. They supported part releases all the way through. Preliminary sizing to detail sizing to part release, so and SCN creation and all that stuff. So they also supported for plugin creation and then resource bench strength, which means a lot of the time we had things that came up and James and the team were able to flex and find somebody who potentially has a little bit of downtime to pick up some extra work for us when we need it the most. So, and that's important because then, we don't have to go hire more folks. We don't have to figure out, when there's less work, we don't have to go figure out what to do with those folks. So, James has plenty of other work for them to do when the need is not as high. So, all right. So the rest of the presentation, we have 3 other presenters. The rest of the presentation is going to be structured like this, and we'll kind of go left to right across preliminary design, weight out challenge, and detailed design. But we kind of wanted to give you all our perspectives on the different phases of the program. So for me, preliminary design, just getting right into it, configuration and material trade studies. Where to design those manufacturing breaks for logistics reasons and for tack time reasons and for assemblability. So that was important. HyperX was important for completing those early trades. I know even before preliminary design, I know Justin and the team were involved in conceptual level trades for material selection and the substructure and all that stuff. So that was how Collier and HyperX team were able to help out there, building the right team. So we have many other programs at Bell that we're fighting for resources for. Early on we identified, hey, Virgin Galactic wants to move very fast. It's a very schedule-intensive program, and we didn't know at the time how we were going to make it work in terms of finding enough people to onboard and train as quickly as we needed them. So, part of the story there is, 2 years ago at this very user conference, I think Brent mentioned Amber and I had attended, and my background isn't stress so much, but I attended because I had ulterior motives, right? I did, James, that's James there. I think him and I were talking about how we could make this work and what the engineering services looks like for Collier, and I think that's where the early discussion started of how can you guys help us in terms of support, on-site support, training, jumping in the trenches with us and doing the actual analysis, and it all kind of went from there. So I think I won that game, though I don't remember. Yeah, perfect. All right, so weight out challenge. This chart here doesn't really have axes. That's weight on the y-axis, and we keep this, historical record of how our weight is changing over time. But the blue is sort of the current forecasted weight, and the red is the risk. And kind of what you're seeing here is over time, our status weight's kind of creeping up, and this huge jump is when Max and Justin and George's team, they completed their preliminary sizing of the boom skins, which are so the boom skins, again, they're the biggest parts on the spaceship, biggest composite parts on the spaceship. I think that the outboard skin we're fabricating it now. We've laid it up. We haven't trimmed it yet, but I think it's coming in at 190 pounds. And so as you can imagine, as that preliminary sizing comes in, early on, we were optimized for schedule. We said, okay, let's make something that yields first pass on the fabrication, which is challenging in and of itself, right? I mean, the boom skins are at up to 60 plies in the forward zones, and all the way at the aft end where they're the lowest loads, they're down to like 3-core-3, right? So the schedule basically dictated that we successfully fabricate first pass. So we said, okay, we got to make this as producible as possible. And of course, releasing the part itself was schedule critical. So we never really had great weight targets, right? We had weight targets early on. I'm not showing them here, but the weight target for the feather was lower than it was on the Unity, than the actual weight of the Unity feather, which was a fully bonded structure, and had no metallic joints for those critical manufacturing breaks that I was referring to earlier. So it was a very weight aggressive solution, and our weight targets were below the Unity targets. So there's a lot of history behind it all, but early on our weight targets were not something that was achievable. So anyway, the preliminary sizing comes in. This blue bar is CDR, and so CDR, we sort of had this chart in front of the chief engineer and everybody, and it was a tough discussion, right? So, after that we had like a 2-week we called it a weight out tiger team, where several key engineering leadership folks from Virgin Galactic came to Fort Worth, and we kind of locked ourselves in a room for 2 weeks and brought in technical experts from Bell and technical experts from VG and figured out, what are we going to do to get the weight under control. And so we came up with this, and George will go into more detail. We came up with a long list of opportunities, and you can see what we decided to do after CDR was we absorbed all of the weight risks, which are the red, and the opportunities, which are the green, and we said, okay, that's status weight. And then afterwards, all the green comes in. That's our list of opportunities that we put together as a team during the weight out tiger team. But you can see since then it's marched down over time. I will say that we've gotten to under our target weights. So we pulled about 500 pounds out of a 3,500 pound feather system. So it's been quite a journey, but it's looking like we're getting there. And then detailed design. So this is the part release burn-up chart, as we call it, affectionately. So this is time on the x-axis and quantity of parts that we have to get out the door each week, tracked at a very detailed level. I'll say at one point we did reach a peak release rate of 55 drawings per week, including left and right hand side. Very aggressive though, very aggressive. Again, lots of night and weekend work. And so at that point, this is where the power of HyperX did help us quite a bit. So we had spent a lot of time setting up our SCNs, as we call it, strength check notes, which is really just a stress report, to accept output straight out of the HyperX database, to where our margins are getting printed right into the stress report. We had it set up real slick, so that definitely helped us quite a bit in the detail design phase. All right, and without further ado, George, turn it over to you.
All right. Hello, everybody. I'm George DeLeon. Thank you for the introduction earlier, Brent. You really covered it well. As he mentioned, this is my first really stint as a manager of a team. For 17 years, I was an airframe stress engineer, or at some points stress lead. So it's also my first time working on a space vehicle. So as you can imagine, two new things happening all at once. It seemed a little daunting. When I first heard that the team was going to be deploying HyperX, that was my one thread to me, honestly, because I had spent plenty of time working in hypersizer, and the similarities to me are, they're striking. So that was a silver lining in running into the team and the challenges head first, is that they were going to be using HyperX, and I said to myself, I can help there. I think I can help organize the team and help us orient ourselves for success. So a little bit about how we did that. So in the preliminary phase, just for time purposes, this was, think back to late 2023. This was fourth quarter 2023. Basically, our structure was in place, not without issues. There were still load path issues internally, which we were kind of teasing out as we put more stress eyes on the substructure. But that's not what this story is about. We were essentially ready to begin preliminary design. I arrived and I said, all right, what's our tool suite? What tools do we have at our disposal? What's our team look like? And the team was on the climb still, so it wasn't completely set yet. But the trick here was, okay, how do we go about aligning our team, aligning all the tools such that we hit this very aggressive schedule. And I'm glad I'm getting a chance to talk and redeem ourselves a bit, because Kerry, as he mentioned, our first stab at it was a little heavy. All right. Even at the beginning, though, we knew the keys to success were really to have a lot of automated structural analysis, but not to mention the automated structural analysis, but also just ease of standardization. We really wanted, repeatable results. We wanted just a standardized approach. We wanted, there was a lot of discussion between VG and Bell on what methods to use, and we wanted it shareable across the companies. Not like appetizers are shareable, but shareable in that we're all speaking the same language, and that's what really one of the big highlights that I saw, that the whole team saw, about making use of HyperX as our tool that we all understand, that we all know, that we can use to talk the same language back and forth. With that said, so that kind of put us in this spot where we said, all right, we want to really maximize HyperX to the level that we're comfortable with. Obviously, we weren't ready to take a dive in every single type of structure and every single analysis step, but we wanted to maximize it. So we got to looking at what that would mean, how that would look for us. Basically, what that meant for us is basically an assembly line of sorts of engineers, basically to handle certain pieces of the analysis. We knew we wanted a kind of a point stress engineer for every part, but we didn't. I don't believe in, honestly, the format of just taking parts, handing them to the engineers, and saying, "Hey, here's your tools, just go and give me margins of safety, and we'll just make it happen. Everybody gets a certain number of parts and go." I don't believe in that. I think, especially when we're deploying HyperX or a tool like this, it's more the way we did it, and this is actually borrowed from a different program at Bell where we used Hypersizer successfully to also move fast. And that was to have sort of a point person that does the initial analysis right up the front, using mostly HyperX for that initial analysis, the acreage sizing, we'll call it. And then, if necessary, we'd have an engineer who's really focused on how to do solution 105 buckling. So that engineer will take the preliminarily sized part and kind of do the next step. And then finally, we'll have either yet a third engineer or sometimes back to the original engineer, an analyst that does the joints. So the joints, all of the interfaces, all the different pieces of analysis that go with joints. But even in that arena, we did supplement to a degree with Excel tools that we have in-house, and there's some reasons for that, which I'll kind of touch on. Yeah, this cartoon. I think this is, in my brain, what designers and stress engineers look like. You know, the designers are a little more laid back. In this early phase, they have, they're working late hours. They got their little lamp. And then, the stress engineers are, we're a little more rigorous. We for some reason, dress similar. We're more conservative. We're more careful. The hard hats. Anyway. All right. So, a little bit of a deep dive into these analysis steps. Right. I mentioned that the first pass, we'll call them point guard, takes the part, takes ownership of it. That's your main point person that interfaces with design. So they're doing the initial acreage sizing, and for the most part, we use HyperX for that entire step. There are some key locations, some we'll call them chunky parts, some detailed parts where we didn't feel comfortable yet with the use of either lug analysis or KT features that we wanted to just deploy other tools that we felt more comfortable with at the time. So, but for the most part, that initial acreage sizing is heavily HyperX. The next step, our stability analysis, was a combination of HyperX and Sol 105, as many of the presentations have kind of mentioned, the use of Solution 105, Nastran. I kind of asked my lead engineers here, kind of retrospectively, to give me their best guess at the percentage, like how much of our stability analysis was with HyperX tools and how much was it with Sol 105. So that's kind of what you see there. It was involved. It was involved technically in every part, not even in the ones where we didn't write our final margin to stability. We still made use of HyperX to down select our conditions. So starting with, as Carrie mentioned, it's the multiple configurations, the extreme, thermal spectrum that this vehicle goes through. It made for a lot of conditions, so it was super helpful to have kind of HyperX to help us really wrap our arms around how many cases are really critical to look at, even when we're moving into the Solution 105 to perform that. And then initial joint sizing. Initial joint sizing, I believe pretty firmly that we could have gotten there. We could have closed that gap and gotten to the point where HyperX was our tool fully. There was just at the time that we were deploying it still some gaps. There were some design spaces where the margin just wouldn't quite line up with our established approach with Virgin Galactic. So we said, all right, that doesn't mean we're not using it because it's too powerful to ignore it, to avoid it. So we're going to use it, but we're going to, as a last step within all of our joint analysis, push the critical check, and it's very specific to what? It was specifically bearing bypass with basically our plug-in for bearing bypass analysis on composite structures. So as it stands, if we had to put a number to it, my lead engineer said about 80% of the joint analysis was HyperX. And then the last one here, it's kind of not like the others in that on the others I'm talking about preliminary design, and that one, it's more about detailed design. So basically, around 70% of our final sizing review and stress notes is the degree to which we deployed HyperX. Okay, so initial projections of our tracking of the feather to our current point, as already mentioned, was not looking good. It was I can't really undersell this how much our backs were against the wall, right? We were roughly 16% heavy, or heading in that direction anyway. And we needed to do something about this. And it was pretty much a kind of an existential crisis to really get that weight down. We were kind of at an impasse we couldn't really be there or close to it at all. So the goal became get 500 pounds out of this structure, however you need to. So naturally, we got to exploring everything. All right, what got us here? Not from the standpoint of pointing fingers at anybody or any tool or anything, but from the standpoint of fixing the problem. So we kind of inspected everything. We inspected whether it was the way we were arranging our folks, the tools, the processes, the workflows, all of that. We kind of came to conclusions that it was nothing related to that. It was all about the methods and the approaches. So what it came down to is almost like as a culture or as a way forward, we were fine-tuned to the KPP of quick turn time, and we were kind of overly focused on eliminating risk of our first pass yield on development of the parts, which is a good thing, but it we kind of overswung the pendulum in that direction, and it was time to really scrutinize that. The other thing is we were moving very fast as we continued to move very fast, and I always say aircraft weight is inversely proportional to schedule. And once again, it proved true. That I know that just from previous programs, not just at Bell, but at other places I've worked, that it always seems to be totally contradictory. And, a constant or a variable there because units or whatever. So something else has to go in that equation as well. So at this point in time, like Carrie mentioned earlier, we had a lot of eyes on us. We had leadership at Virgin Galactic, leadership at Bell. We kind of all got closed into a room, and we said, all right, throw everything and anything, any idea you have, put it on the whiteboard. Let's start talking about it. Let's start thinking about it. That's actually a picture of four different walls in a room that we just filled up. We probably ran out of room. Not intended to convey real information pertinent, but just to kind of state that we had, this was the moment to put everything on the board. Basically, go back to square one where we needed to, but also don't forget we have to do whatever it is we do to solve our way out of this. We got to do it very fast, and now even faster than originally. The bottom right corner there is kind of our design of experiments, if you will, just a hand hack at it, because we knew that we wanted to know how some of these weight savings ideas interacted with each other and all that. So, okay, so with that, we could not just let it be the the Wild West. We couldn't just take ideas. And again, I don't believe in telling all the engineers, here's the ideas, go, run, do it, do them all. No, we had to kind of study them. We had to wrap our arms around them. So this is intended to kind of help describe how we went about doing that. That's not a martini glass. That's a funnel. We'll call it the funnel of sanity checks. Basically, we pumped all the ideas through studies. So we had all hands on deck, not just our Collier friends that were at this point working alongside us, remotely or even during a lot of visits as well. But some of our people. So at this point, I like to say it was kind of HyperX's time to shine because we were up against it, and we needed a way to explore and study these different ideas quickly and get them characterized and get real weight savings potential on the table, so we could know exactly which ones to deploy and which ones not to. So the way that the studies worked is you kind of put it through. We used whatever parts had some progress on them already, like the boom skins, for example, were very good candidates to. They were a good kind of proving ground to test out some of the ideas, and then we just scaled up, to the best that we could to the rest of the parts. And what we were after is, okay, let's test these ideas, but let's try to also assign a risk level to them. Let's assign a schedule kind of factor to them. And if they passed our check, and that means the ones that you see down here these were deemed, okay, let's go after those. Those look doable. Those look, they come with risk. They obviously did, because we would have employed them earlier if they didn't. But they come with acceptable risk. On the right here, I've got the kind of some of the composites ideas, some of the metallics ideas. And in this chart, I'm just roughly trying to demonstrate, I guess, with the diameter of the weight savings option, kind of roughly indicating relative weight savings available. And then the ones that didn't quite make it, I'll say we didn't necessarily say, okay, no, never. We just said, let's put them to the side for now. And we ended up calling these kind of Group B weight savings, Group A weight savings. The Group A, we were just going to do. We're going to incorporate them and organize ourselves to go ahead and put them into motion. The Group B were, a little more costly or a little more time consuming. One is just straight up more schedule. That is the idea. Just take more time. Multiple presentations today and yesterday just talked about how if you just keep going, you can save more weight. But we didn't have that time. But it is a Group B option that we had, such that a given part, if we're not meeting the target, there's an option still. Let's go revisit it. Let's just kind of sharpen the pencil on it. It would be impossible to tell you guys how many, and really describe in that much detail how many ideas we came up with. It was more than 20. And the way that the team performed and knocked these out, it was pretty incredible. Not just our team, but the Collier team that was on board helping us. There were cases where we'd still be in that meeting room with the executives, with the leadership, chief engineer at VG and everything, and we said, well, we'd really like to understand, this one or this other one. Maybe it was including uniaxial tape, along the lands of caps, or just shifting gears on a safety factor, not a safety factor, but a uncertainty factor that maybe we were a little too conservative on. And some of these studies came back in a matter of hours. I put them out there just through Teams. Like I said, we were truly locked in this room. There was no getting out. We had to make the most of the time with all the leaders in town. But I'd send it to Max. He'd send it to Justin, or he'd tackle it himself, or any one of their guys would tackle it. I'd dish it out in the morning. By lunch, I had an answer. Oh yeah, by the way, we can save maybe 10 pounds if you scale it up to the vehicle on whether it was laminate family revisit or ME layups. Okay, all this said, even what I just mentioned, getting these studies completed, getting them organized, that's not quite everything, because I'll try. Well, at the risk of, manager going to talk a little bit of detail here. So if that's something you got a sensitivity to, this is the time to avert your eyes. Otherwise, stick with me, and it'll be over before you know it. So basically, what I'm trying to explain here is these two metallic options. One is to sort of improve the way we do orthogrid buckling, of the webs, so the pockets. So basically, we know that assuming simple support where the uprights are, where the fasteners, not the fasteners, where the stiffeners are, is a simple solution. A lot of different companies do it that way, and it's not a bad solution. It's not super heavy, in my experience anyway. But since we're looking for every ounce possible, let's go ahead and make use of the HyperX option to improve the buckling fixity. So we wrote a quick plugin. Our guys wrote a quick plugin, basically putting into it an established VG and Bell solution that quickly calculates a better buckling fixity than 0, taking into account the shape, so like the height and the thickness of the stiffener. Okay, great. So we put it into play. We got our weight. Maybe it was 8 pounds, let's say, when you scale it up to all our metallics. Problem is, at the same time, we're also looking at weight savings from machining min gauge, and there are areas out there where our stiffener may already be at min gauge. So you can already see a problem here. It's kind of circular, so you're not going to get all the weight savings. So before just reporting out to leadership, hey, here's the total amount of weight we can get out, we said we got to deal with this problem. We have a lot of overlap, a lot of losses in trying to make all of these, trying to pump all of these weight-saving initiatives into the design at once. But at the same time that we realized we got a problem, we kind of said, wait a second. We got a solution too. We got databases that we can run with all of the weight savings initiatives at once, or even combinations of. So without, and this might be, for me, in my section, from my perspective, this might be the biggest takeaway from how we went about solving our way out of this problem, is that without HyperX available for this either leads us to the wrong answer. And what I mean by that is we pump the brakes too early. We don't look for more weight, and we start moving. Or we just slip schedule badly. I think what we ended up doing in a matter of 2 to 3 weeks would have taken easily 2 to 3 months, if not more, with other tools. So, okay. So coming out of all of those studies, we kind of came up with this workflow. And again, I've got kind of all the pieces of the workflow where the HyperX tool is kind of involved in. So, like I mentioned, we had Group A sizing ideas, Group B sizing initiatives. So this is the way that we ended up kind of treating every part as we went through our sizing. We would start with our Group A sizing. Okay, do it, just size it, implement all of the approaches that are going to save us weight. And then, all right, let's check the part. By this point, we had spent time developing part-by-part weight targets for really every single part. Obviously, the important ones were the really big parts. We had high focus on the part-by-part weight targets on things like boom skins. So if it didn't pass your target weight, your limit weight, well, is it the end of the world? I don't know. Let's see. We go down, we review the limit weight. The reason I have a HyperX kind of box next to review the limit weight is because HyperX was involved in performing those studies. Those limit weights, as they stood, leveraged what we thought we could do out of those studies. So it was involved. Maybe there was something up with how we performed the study, or maybe something else. Maybe we just got too aggressive with that one. So okay, you go through at least that sanity check. All right, is the limit weight valid? No. Well, let's go ahead and adjust it, whatever it was. Let's put a fraction on it, even to the point of let's find weight in another part within the same assembly or something, let's say. If it is a good limit weight and we really need this part lighter, all right, it's time to look at kind of weight out sizing Group B activities, whether that's just passing back through, iterating a few more times, whatever it is for the part. Okay, so moving into detailed design, we got what I call the road to landslocked. Oh, and just to introduce you guys to, well, you've already been introduced to this little key, but Bell engineers in the red hats there, Collier engineers in the blue hats. I was doing kind of a practice run of this with one of my engineers back home. The feedback was literally, George, I think the hats are a little political. I said, I didn't write anything on the hats, yeah. I'm just observant. Our company logos are blue, and, our Texas home bell is red, Nothing political, I promise. Anyway, so what I mean by lands locked is there was a really high importance in maturing the boom skins. You already heard about the scale of these things. They've got basically 22 or so core stiffened areas and just, numerous substructure components attaching to them. And the path forward and the path to really open up, we used to call it open up the floodgates, was to get those dang lands sized, final sized too. Such that, if you're talking about a substructure composite part, the IML of the boom skin was not the tool surface. Our boom skins are female tooled. That the IML of the boom skin made up the OML of the substructure part, which are tooled on that side as well. So we absolutely needed the right surface there. So really, kind of nothing could progress forward to final design, especially substructure, without getting that right. So I guess I'll go kind of one at a time. And in this case, the hats are sort of indicating Collier versus Bell involvement. So I'll just tee it up this way. This was a point in time with where we could have easily shied away with how involved Collier was as a partner, as teammates. There were leaders asking us, hey, is it time to pull back the boom skins? Do you guys want to tackle this phase and maybe give them substructure parts or something? And I give a lot of credit to Max here. As we talked about it, behind closed doors, now to everyone, he said, no, these guys have gone through iterations. I know we had a high weight skin, but nobody knows it better. Nobody knows the process and the sizing. With our guidance, let's keep them very involved and just, let us do the talking to the leaders. No, this is the way we need Collier, we need the team. And there was a lot of pressure on them. I mean, you can hear that from Justin and team. But they did it, man. They were up to the challenge for sure. So at this point in time, we were needing all of the weight studies to close. There were some trickling in still. There were some even material trades at this point. Those were all kind of coming to a close. And we needed sizing of all the boom skins. And I mean almost every aspect of them, especially joints and acreage. The buckling, we kind of determined that some of the buckling could kind of come in after, but really we needed iterations done, and we needed the joints and the acreage to be very, very firm. We needed to call that final. As we got to that point, so we also, as I mentioned, we needed to make sure that we had high confidence in what those joints look like. Another key point I want to make here is that, if you're just looking at a cross section of the feather and you've got, boom, inboard and outboard boom skin and a big, rib or substructure rib or whatever it is, a shear web, you would think intuitively that the material wants to be in the skin. You got your outer fiber. Let's pump in the material. That's going to make you more stiff and handle the moments better. Something that we learned through our process and through the interaction, not just between Bell and Collier stress, but between Collier stress and Bell design, we were interacting and iterating so much in this stage and even the stage before it that we had learned something. We learned that the material being in the skins is not necessarily the lightest, and actually it was costing us weight. This is something that wasn't discreetly in a study. It was more like an observation. And we said, you know what? We need our caps to be taking some of the load. We need these well balanced, and maybe we even need them thicker than the skins in many areas. The reasons behind that is that we've got ply drop rules. Every company probably has their own kind of discrete set of rules for how aggressive to reduce the layup. And if we went with an approach where you just pump meat into the land for the skin, you end up essentially trapping weight because it takes so much distance away from that land to get that material out per our own guidelines that we were kind of eating more than we wanted to there. So without the amount of iterations and the just the abilities of the guys, but I mean, the iterations with design as part of it, I'm anxious for you guys to listen to Justin's part, where he's going to talk a little bit about how that interaction with design happened. Without all those iterations and all that time looking at it, this doesn't jump out at you. This is not intuitive. So we just leaned in. We said, no, let's just try to put meat in the caps and make it part of our weight savings approach. So, all right. Okay, finally, kind of repeating the part release grind that we saw earlier. I can tell you that essentially, I know there's no scale here, but in a matter of 4 months, I'd say 4 to 5 months, we got through our detailed part release, our 500 plus parts that make up the feather structure. How did we do this? We just collaborated across all the companies, VG, Bell, and Collier. We trusted our early decisions. There was no backing down from it. Whatever we had put in as our process and how we had kind of aligned ourselves, it was time to just double down on that, and that proved dividends. And then so we established we followed our established processes, and we didn't forget to enjoy the challenge. That was something that I'm sure was hard to hear from my team when we're up against the wall facing this impossible challenge. I said, hey guys, this summer this is last summer in this case I'm talking about. I just told them this summer, it might suck. We might be, putting in some crazy hours. We might find ourselves pretty stressed. But at the same time, it may just be the most fun you ever had in your career to talk about this later on when we succeed. And so, anyway, it's really cool to be here telling you guys kind of about how we approached it and how HyperX was used with manager level details. But I'm excited to let the next two guys, which I consider just absolute ringers at stress analysis, go a little bit deeper and give you the real details of a few of the examples of how we went about it. But I mean, I can't state enough how we were operating basically like a machine. At this point we had the hats on, different orientations. The blue and the red at this point had crossed aisles. We're working alongside each other. So yeah, it's been fun, and it was just amazing to have HyperX and to depend on it as much as we did, and to challenge it the way that we did. So with that.
Hi everybody, I am Max Silva, stress lead on the Virgin Galactic program at Bell. And I love when my managers talk about how easy things are, package here, moving things around. But with that being said, today James said something that is very important. HyperX was created for stress engineers, right? And to get to the point where they were presenting for you, there is a steep curve, especially using from a conceptual phase all the way to releasing. One thing that is funny to mention that Kerry was trying to find people within Bell that could join the program, right? And he found the most experienced people, very nice people. I know them all, like them all. But our average year of experience was 20 years. With that, it comes all that traditional background that we want to have a FEM, extract load, put on our in-house tool, and just get it done. But why not use HyperX? You guys may be thinking about it. Because they failed to say that when we joined the program, we had no sizing loads. We're using a FEM from a program that was canceled by VG for reasons that I'll let them speak for themselves. Sizing criteria, not defined yet. It was a moving target. It was like, it looks like they were playing a game, like pushing one side or the other, whatever makes things faster, right? And on the top of that, you're asking all those old timers to jump to a new software that some of them never heard before. So how do you take that if you guys are in my position? One caveat, no official training. Training in HyperX was the material that comes when you install the software. We're meant to receive load somewhere end of May, then went to June, July, August. By September, we had it. Preliminary sizing was done by December. And pressure zone. It was super aggressive. Schedule was so aggressive, a few times George wanted just to call the cops. He couldn't take anymore. And that's how we are talking about. But it was up to us, the stress engineers, to figure out how to use the tool. And that's what I did. I thought everybody was doing the same, but that's actually what I did. So, as you can see here, still in the preliminary design phase, we needed to do something about it. So my lead comes to me and says, hey, instead of waiting, why don't you just go ahead and start going through the training material that comes with the software? And that's exactly what I did. I was just trying to be a nice guy. I didn't want to fight him. Went ahead, read the material. Like, it took me like a morning to read the material. Got bored. I'm being honest. I go, that's not really going to work for me. And the reason behind it, I've done, after 22 years, I've been to so many trainings that whenever you're opening the file that comes with it, everything works. So at this point, I'm using a FEM from another program, right? I don't know what's in there. The FEM that we are using, just so you guys know, the substructures didn't have caps at all. Just because of the way they assembled the previous aircraft, everything was bonded as is. There was no caps, no fasten, nothing was there. And they are asking me just do it. Just apply a factor and just do it, right? And okay, so read the material for about half a day, and that thing was clicking on my head. That's not gonna work for me. So I decided, okay, instead of doing that, I'm still gonna go through the training, but I'm going to push the FEM that we have available to us through it. The goal was not to size a part, it's just to see if I know how to use HyperX and make it work. What I did, if you see the little trapezoid or the blue, that's not a cutout, that's just so you guys have an idea of the size of the part. So I chose one of the smallest substructural parts in there. That's a rib, upper mid rib, that's what we call. And I'm going to push that little guy through HyperX and see if it works. Again, just following the sizing. Didn't know what to ask for criteria, select them all. I'm just going to push everything here and see how it goes, right? It didn't go well. Because our material didn't have all the allowables and all this stuff. I said, okay, I cannot do that. So what I did, I contacted one of my buddies in a program that George was, because I got to the program before George. Hey, can you share the full criteria that we have there for composite? Okay, he shared the criteria. Then I compare against our allowables. So that became my initial criteria to check stuff. So I was just being proactive, doing my own thing, right? And in my head, this is a new tool. It looks nice, the interface. It looks very friendly. The material is actually easy to read and to follow through it. So plug in, pim, pim, boom, boom, sizing, happy, right? They don't care about the number of plies. We're still using effective laminate. They don't care about anything. As long as it runs, I know I can work with it, right? So that only took me about an hour. And I was like, did I miss something here? But the thing was just a plain web. So okay, it's just a flat. So something might be right here. So this time maybe I should go for something bigger. So I took this 30-foot long skin. I'm gonna push this through it and see how it goes. But this time around, instead of just trying to look for a pass for HyperX, I'm gonna actually try and size it. So Kerry mentioned that was a 60 plies at the very beginning. What you see here at the very beginning. But the skin has cutouts, it has cornering, it has modeling effects. So when I first pushed this through HyperX, I got something like 300 plies in some locations, right? And I got scared. I'm not sharing that size. Whatever it is, I don't know what I did. Let's just keep going and revisit this layer, right? So within 3 days, I was able to go back to the FEM, identify hotspot locations, and make a decision to use like average loads or exclude elements because of modeling effects, triangles, and the way how things were modeled on that FEM. Still, that was part of my training. So what I do next? Jump to the other skin. Because that's not a single skin. There's two of them, inboard and outboard. And on the top, we have what we call upper skin that looks like a leading edge, and it just connects them together. So I got so excited, it felt like I was playing on PS5. I kid you not. I was so excited about HyperX. I can press, because before, it took me like months to do something like this. Now I'm pressing a button, boom, things are happening, right? I got very excited. I start sizing everything. I'm not even talking to, I'm not talking to them. I'm just sizing it, right? I'm just there, look at me, right? I'm sizing stuff, right? So, and they keep going to those meetings that people are very angry and all this stuff. And I can see on their face, and now I ask Carrie, remember, don't put me on those meetings, then I'm fine, right? I don't want to get involved. I don't want to get involved. But one of those days, I hear a design lead complaining that they were against the wall because they haven't received any sizing. And then he was my friend. I've worked with him so many other times, so I decided to, hey, just between the two of us, I sized the skins. But here's the catch. Oh, by the way, I was able to reduce from 300 plies to 100 something at the corners. I just share with him. Like, that was my goal, just to help him out. After I did that, lots of people on my desk. What did you do? How did you do it? And all of a sudden, I'll have to defend myself because I just went over the material, now I'm sizing stuff, right? Okay, that's good. So I was able to defend myself, share the information, and also one of our leads had some experience. She was here 2 years ago. Share the information that of what I've done with her. Then a couple of days later, became the most experienced guy. Within a week, I went from not knowing HyperX to be training people. Now I'm in charge of training. And now I had in my hand was Charlie's phone number. So he's not even here. So they told me, go learn HyperX, and here's a phone number. It was Charlie, right? And I'm like, how do I do this? Okay. So, but anyway, I like the challenge. No big deal. So I start training people, and as I train them, they start getting angry at me. Oh, but how are you doing this? How are you clicking stuff? I said, did you read the material? No, none of them did. They just wanted me to show how to click stuff. And one time, George also asked me, hey, Max, show me how to do the HyperX. So I go to his desk, and he starts clicking stuff. And then I just tell him, if you stop clicking, ping, I can't help you. Because he was just click, 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 click. It was so fast, I couldn't even do anything for him. But anyway, so that's how my involvement with HyperX started. 1 week of experience, all of a sudden, I'm the guy, right? But here what happened when, for me, to train them and try to convince them. They didn't take that easy, right? They wanted to understand why HyperX gave us margin of safety. They were not comfortable with that, seeing plots of margin of safety. And I asked, what is the issue? Well, we don't know if it's capturing the hotspot. So what I did, this is not part of the program, by the way. This is a different program at Bell, this part here. So what I did, I started playing with HyperX. And you see two plots here. They're fairly identical. One is a margin of safety summary from HyperX, of course. This one is actually from Patron. So this one comes from Patron. If you switch how you see your stress levels, you can do an element field and stuff. And you can see on this one, they're very similar. They're actually hitting the right spot. So I had to present them by example. Hey guys, it is doable. Just give it a try. And that's what I was trying to do. It's okay. So they took it. They're taking well. They're still complaining, coming to my desk every day. A big line in there. Just when you go buy cold cuts, they need to get the number. That's how it was. I became a 1-800 call. Instead of calling you guys, they'll come to me all the time. But anyway, that was fine. But we still need to validate and see how the tool pairs against the Bell way of doing analysis. So there was a major thing, major setback. Some people were not, no, I mean, we do this is the Bell way. I said, okay. So after training like two very experienced guys and one young one, we decided to do a deep dive. Let's go do a deep dive and understand everything that we need. So for every single criteria that we need to analyze for, we are doing a hand calculation and pushing through HyperX. And we're matching the numbers. If it doesn't match, that's when we start using Collier. If it doesn't match, we need to do something. We didn't have enough people to write scripts and plugins. So management decided to start using them. And they start coming. That was about the time that they start coming to visit us. It was Brent. He came just to buy hats, by the way. Everywhere he goes, he buys a hat. Justin, Olivia came later on. Then we got a team. It looks more like an army of Ryan, Brian. We got them all. We just got them all. Every single one that lives in Riley. I don't even know if they work for Collier. If your name was Ryan or Brian, we just welcome you, give you a badge. You're probably with them, right? But anyway, we started doing a deep dive. But like they mentioned, we didn't have time. The luxury of time was not on our side at all. So if the numbers doesn't match, there is not something, a coefficient or something that we're using, it does not matter. It's gonna either become a plugin, and this was because of lack of time. It was either gonna become a plugin for Bell or a script. We didn't care, we just don't have the time. We need to get this out by the end of the year, right? And like George mentioned, there's no target weight. So this is a dream for any stress guy. That means I can make the thing as heavy as I am, and everything is good. So who cares? Like, I'm just pressing the button, sizing, and just releasing, right? So anyway, material curves, also not on the database. I found out the database that we have been used for a while was not done by a stress person. It was just somebody that was enthusiastic about HyperX, and they just combine all this stuff. Big deal there. So how do you resolve all this? How do you start building a database that can be shared? So at this point, I brought everybody up to speed with the help of our friends that were visiting us and teaching. much better than I could teach our stress analyst, we decided to use enterprise database. I know that most of you guys may not have used it before, but that tool was key for our success because we were able to split the work among everybody, and we had a coordinator that was in charge of the main one, right? So we create this child database. People go, analyze, tweak the information any way, shape, or form they need it, and then the coordinator will absorb that back. If that was required, was something that we could, or something that we have to implement, we would absorb it. If it was something that was already on the database, we just ignore. So that was a key component for us to start building a HyperX database so we can analyze. Material curves, that's something that we sent to Justin and team to help us out. We just send all the technical data. Can you just put that in there? Everybody was busy investigating, turning. There was no stone unturned when it comes to matching numbers. So everybody was all hands on deck to get this out. And there was a few people that were sat on the side that we said, we need a new FEM because we cannot continue using a FEM that is not from this aircraft. So, or spaceship, need spaceship, otherwise they get offended. But anyway, and that's how, that's what was happening for us, stress. They were discussing other stuff, but we were like, we're going crazy on our side. So the conclusion, even before we start sizing stuff, just so you guys have an idea, we went from a FEM that is very simple, and we are trying to maximize the usage of HyperX. That was goal. If we were to achieve all the level of usage of HyperX we needed, we need to refine the mesh, have all the details, so we can push as much through HyperX as possible. So refine the model, model fasteners, and walk away from effective laminate and start developing families. Wait out. As George mentioned before, it was a scary moment at Bell. So as they were locked in a room for 2 weeks, deciding everything, I was in charge of making sure everything was being done, pretty much a live stream, right? I had ears inside, which was pretty much George and Amber, and they were like texting me or IM me, do this, we need to know now. So I had hours to flip stuff for them. Other than changing material that we can push easily, most of the stuff that they were asking us to do would take weeks, if not months, to do it. But we decided to go 100% HyperX. We can pass on HyperX. We just show it the potential. We're looking for the potential. Can we save the weight or not? So, and thankfully, we had HyperX on our side. Otherwise, we wouldn't be here today on the conference, of course, but we wouldn't be finishing the program anyways. I got the red light, guys. So that's my final slide anyway. So once we walk out of weight savings, we had the process, right? We had the experience now. They were scared. They still have to meet a deadline and stuff. On the stress side, all those people that were concerned about HyperX, we had that smirk on our face. We were just laughing because we knew it was possible. We had the setup, right? We know that we could do strength sizing almost 100% in HyperX. We had our joint analysis set up. Everything joint-wise goes through HyperX to a certain extent. We have the shear, tension, and bearing in HyperX. Everything else we made into a script or plugin. Bearing bypass is the only one that we are forced to use outside. That was a decision, not by us, by VG. They wanted to use their tool, but we still export the data, put on their spreadsheet, good, move on. Buckling was also a decision at the end to keep doing global buckling outside. Once we do that, if we need to update the FEM for any reason, well, we do it. If not, we kick out the stress report. Stress report, as we are going through the process of investigating the tools, we develop a stress report in Excel. That's very cool. It actually reads the output files from HyperX into it, populates everything for us, and it shows the hand analysis and the HyperX margin side by side. So for each critical margin, we have 2 margins of safety. They also became a way to check the analysis fast. If they match, good. That means it's good on both sides. If it doesn't, then we go there. Most of the time it's because we're using the wrong temperature. Then we just switch to the next temperature, and we just keep moving. The reason why we still do 30% is because we still need to do nice pictures, introductions, and all these little things that we do on the stress side, but that was also automated. And just so you guys know how powerful this is, right? Just one more thing. Coming out of weight savings, leadership was scared, and they wanted to release at least 2 lofts as quick as possible. Going to this meeting of Kerry and George and everybody, all the leadership is there, and they're talking about, can we do it, can we not do it? I already have the process, so I'm fine. And they are asking, 1 a day, 2 this week, stuff like that. So I said, I can do 1 a day. And then they look at me, oh yeah, Max, maybe we need more people like you. Just kept quiet, and I said, okay, I can do it. So in between my meetings, remember, I'm a lead. In between my lead activities, I was able to push 5 parts that week. So it is possible, it is awesome, and I'm actually very happy that these two exist. I was waiting for these two for 22 years. Thank you, Justin.
The light just kind of, okay. All right, no time. All right, so yeah, I'm gonna kind of continue the discussion running through each of these phases. Kind of focus on, I have this slide up, but I'm gonna kind of run through it quick. These are just some of the things we provided Bell through our engineering services. What I kind of want to focus on today, though, is the tailored workflow automation and optimization. You know, we would go to Bell, we would see what their processes were, and we don't want to just brute force ourselves in and say, this is what you do, this is how you do it, see you later. We want to see what their team's used to doing, and then see how we can leverage HyperX to help them. So, actually, all my notes are done, so I'm gonna go here. I don't know what happened to. Oh, wait, I see them. They're all kind of off to the side.
Squished it over on the side. Yeah.
Where's my mouse?
Don't have one.
Don't have one. There it is. All right. So, for the preliminary design, as you've heard, we had a pretty large challenge of, we have 2 main kind of subsections, with each have many parts to design, to size. I think initially there was, 50 main parts. That's not including all the fittings and just these smaller parts. Rapid onboarding of analysts, as Max said, he had a little ticket taker of people coming to him. We started our on-site visits. We were doing on-site training, virtual training. We even saw some Bell-led seminars. There was Metallics with Matt or something like that. There was,
Composites with Collier and friends.
yeah. As mentioned, analysis guidelines and best practices were all being reviewed and documented. Material data was going into a library. And while all this is happening, the clock's still ticking. The days are going by, and that schedule isn't going to pause for that. So we needed to find a solution to kind of help expedite things. So obviously, as we mentioned, enter the enterprise database use case. As a couple of people have mentioned, you can pull in a GFIM and split it up into multiple parts. I'm going to kind of gloss over some of these things because some of these have been mentioned already. But first thing we did was we implemented what we called an integrator. This was somebody at Bell. Their first task was to control what we call the company database in this case, the templates. This holds all the material data, the analysis methods, everything all in one place, making sure that's all up to date and pushed out to the team. Second responsibility of the integrator is actually managing the main group database, and then they would split that up into subsections, and if needed, those subsections could be led by an additional section lead, or that initial integrator could maintain it themselves. Along with that, making sure the shared folder was kept up to date, as well as working with management to coordinate the part sizing schedule. So making sure analysts were getting the right databases when they needed them, and then make sure they were getting them back when they needed them. So with that, you have your typical breakdown. We use the include file structure to create these databases. We use the ability to read-only structure, so analysts could get an understanding of where loads were coming in, interfaces, things like that. I think the kind of big takeaway here was this allowed users, both as experienced as Max was at this point, to the experienced analysts that's never touched the software, to I think some pretty new analysts that were coming on, maybe to Bell or the program starting out fresh. This was basically a quick start tool where the part was loaded in, all their methods and materials were set up, and all they had to do was, kind of go through the training of zoning things out, how to assign properties, which toggles to switch on their analysis properties, and then from there, they could just go. On top of this, it also allowed for kind of quicker review of the work as these databases were absorbed back in. As you've seen, we do throw the kind of a change log of things that were, might have been updated. If those are not approved, you don't absorb the database, you kick it back and say, hey, this method isn't approved, this approach isn't approved. So, you need to correct that. Otherwise, bring it in. And you could also iterate this process with HyperFEA. And so this allowed us to kind of large-scale disperse parts and keep things on track. So moving on to the weight out study. As mentioned, as we all know, so this y-axis is weight savings. So you can achieve more weight savings, but with that, you do take a hit to the schedule. For this weight out study, there was the need to rapidly identify areas where we could do targeted optimization. As the time clock is ticking, there's costs that are, being hit, just resources, schedule costs, all that. And so what we can do is apply HyperX to this schedule, and as we've mentioned, kind of help pull that to the left, and you see here, you can achieve the same weight savings, if not more, in a quicker amount of time. Several people here have kind of discussed the options there, the quick trade studies, things you can do, material trades, configuration trades. But what I kind of want to focus on my end is what do you do when design comes in and does their work? You could optimize the part all day, but if they can't build it, then it doesn't matter. So design's going to come in and do their work, and we're gonna take another weight hit from what they're doing. And so this was another kind of identified point that we realized that we needed to find a way around to hopefully bring that red X, closer to our initial target, while also shortening the time spent. So what we did was we started very heavy collaboration with the Bell designers. This was both us on the Collier side, and then talking to the Bell designers, and then Bell Stress with Bell designers. And basically we had this iteration, this process of passing essentially boundaries back and forth. From HyperX, you've got your zone boundaries. From CATIA, we've got grid cell boundaries. We would send, our optimized zone boundaries over to a designer, and they'd say, yeah, that doesn't really make sense. I need to shift these over because I can't do ply drops right here. Can we do that? And you do a couple passes, and you kind of finally land on something. And what this kind of helps us do is it kind of helps us get ahead of the work. It lets the designer get ahead and start thinking about these things, because they've got an idea of how many ply counts are going to be in this area already, because they've seen the numbers. Their hope is it's going to go down, but they can at least get a feel for where they need to maybe try to be more aggressive with their ply drops, see where we might need to take in a reduced allowable from that fact, things like that. So we can keep sizing as they kind of work through their processes of doing the ply sequencing, which will then be passed to manufacturing. So, but what else can we do? It's kind of hard to see here, but we were also able to link our zones to these CATIA grid cells by name. Through scripting, we basically had each zone mapped to a grid cell, and so we were able to take the grid cell that was named by design, absorb it into the database as a HyperX zone name. So with that, we were able to develop a system. Bell had I won't say a particular way, they had a specific way that they were doing their ply books. Over and undercore ply books were actually separate. I think our native methods just spits out one. So we actually had a scripted process that would kick out an over and undercore ply book. And since we had this zone to grid cell name mapping, we could pass design a ply book, and they could absorb it directly into their model with all the ply counts. And that process could also go the other way. We could take a ply book from design and bring it right back into the database, update ply counts immediately, and get new margins for areas where they've either increased plies, theoretically getting a better margin, or maybe there's an area where they wanted to reduce plies. The big point here is to basically try to eliminate the transfer of data through PowerPoints. I will say at the end of it, we still did use a good bit of PowerPoints just as like kind of quick reference for people to kind of go and look at, so they didn't have to open up a database or CATIA. But this was one of the quick ways we were able to update models between stress and design. All right. So then we move into the detailed design phase. For here, we've got part release. We have a need to be able to rapidly update our analysis model to match the CAD model. We need to, as closely as possible, represent the as-built parts. We need to stay aligned with any revisions that are happening, make updates quick, see what's going to work and what's not going to work. We need to mitigate any negative margins that might pop up after a FIM iteration, as they tend to do. And then also we've got assembly releases. We did the part level joint analysis, but we've got to do a full assembly release, basically ensuring the joints between design and stress are aligned. With this particular section, we had 10,000 plus fasteners that we were having to manage, that we tried to keep same within the bay, but sometimes you just have some peaking areas that kind of drive fasteners to size up in areas, and you can't really avoid it. So how can we do this? Like I mentioned, traditional methods use PowerPoints prone to human error or just misinterpretation in general. And so one of the things we can do is just simply importing CAD geometry. This is a pretty straightforward picture here. We basically take the individual ply boundaries from the designers and we pull it into our database. And here we can verify that our ply counts are correct. We also have the opportunity to, if we have a couple elements popping up negative, we can kind of go in and dig deeper and see if one of those elements happens to fall in an area where we might have more plies than we think we have, based on the zone-based analysis. I think my assigned designer was really happy when I stopped asking them, through an email or a text, how many plies do I have at XYZ location, getting 5 to 10 of those emails a day where I needed an answer quick. So that was very useful. Another use case I don't have a picture of, but bringing in solids. The as-built part has drain holes. It has borescope holes for inspection. Some of those are not modeled. Our notched allowables, can go up to a certain hole size, but, someone gets a drill in their hands, they like to drill as big of a hole as they can. So make sure you've got the appropriate knockdowns there. Make sure the analysis in that area is, substantial enough to account for that hole. Unfortunately, we were not able to use this. Sorry, Bell. But I did want to highlight, as August had shown yesterday, this was something I wanted to implement, but just with it being such a new feature and our schedule, we just didn't quite get a chance to go from stress to design. But, definitely next project we will. But essentially this is showing the as-analyzed fasteners from HyperX, sending that data back to the designer. I know this would have saved a whole lot of headache if we had had this capability at the time, because again, we were using PowerPoints, and we spent a chunk of us spent a good amount of time reviewing those PowerPoints versus the CATIA model versus the HyperX analysis. So this is something that would have definitely cut a lot of time off several analysts. But so how can we take what design has, though, with the joint analysis, with these 10,000 plus fasteners? How can we take what they have and leverage on that end, on our end? Bell had an existing process. They used basically these CAD vectors, these just like line vectors that design would send them. And they already had in-house scripts that would create a spring element, apply a property based on that, and then assign the correct stiffnesses to the joint. And so I started kind of digging into those files that were being sent over and noticed that design was nice enough to also include the fastener type and diameter in there. And so this was actually a really simple thing. Bell was already using this fastener type to determine the fastener stiffness for the P-bush card. It was a very simple update to their script to write in a comment per P-bush that HyperX can read. We can read in preprocessor comments, in this case hypermesh comments, as a P-bush name. And when you load it into the database, it tells you this 110-223-6. That is a fastener type for this location. And so along with that, we've also got, we can read on our CAD and we can see their line vector also has that name attached to it. And then we just happen to have that fast in our library because it's the correct one. So So now we have a way to verify we have the correct fastener between design and stress. We can take this one step further, which we will be doing probably next week, it sounds like, at some point. I don't know.
You're not doing it in the background right now?
Oh, yeah. Yeah. The other me is back at the hotel doing work. But we can script this process. We have a joint design property here, and we have the fastener type, and that's a pretty straightforward script to just go in and read these thousands of individual HyperX point joints and assign the proper the fastener type, which really beats looking back and forth between a PowerPoint, as I have done many times. And so I look forward to utilizing this again and again. So let's see. I think that kind of covers it. So kind of just to wrap this up, as you can see, from beginning to end, we can assist you in the HyperX deployment onto your project, kind of streamlining that process, figuring out what your automation needs are, any plugin scripts you may need to match your analysis methods, and all these things. And with the last bullet point is making sure we're helping keep you on schedule. That's what we really strive to do. So I think with that, that's it.
Okay. Okay, we'd like to open it up for questions, and since there were 4 together, we're going to do it as a panel. So if you have an open question, they can choose who to pick, or if you have a certain question, just name the person.
Hi, great presentation, by the way. And just to be clear, not picking sides, but this is probably a question for the Red Hatters on stage. Earlier, you're showing the sanity filter on, why you're picking certain designs or options on trying to fix some of your weight issues. Why did hybrid laminates not make the cut?
We did. This was a very complex loaded structure we found. We did a lot of trades very early on, actually, and this is a trade that kind of kept coming up. But a lot of the structure, didn't have a primary loading direction. It seemed there's a lot of, bending and twisting. Once this thing is dropped from the mothership, they light that engine, and then, that flight pattern just, like I said, the loads are so complex that from what we saw, study after study, and then based on, the added complexities of manufacturing, it just didn't seem like we could really validate that extra kind of hit to that the schedule and time. So
There is one example, though, Jonathan, where we did actually have it. We took it pretty far, and we encountered, high concern and reasonable concern with Bell history on the features that we were trying to roll over with the layup. So we made a late game change on some substructure, along some of the high loaded shear webs, kind of as you lead to the tusk area, which is where the unlock feature is for the feather. So we tried and ended up having to pivot.
Yeah, okay, thanks.
A great presentation. I can recognize that might want to hold some data back from us all, but can you say how many heads you had on this for stress, and what maybe the ratio between heads and licenses? Because did every analyst have a license? And then I got another question after that.
Yeah, I think we had about 30 designers and close to 30 stress folks at one point, including the Collier team. So yeah, it was really about one-to-one. And I think, George, I'll let you elaborate on that too. But the other question was licenses. We must have had about,
We had 10, but then because of other programs, we decided to expand, and the Bell ended up with like 20 plus license. When V280 started to try and use it.
Yeah, I mean, our licenses are shared between other programs.
At the beginning was about 10, and
Then my second question was, y'all went from a smeared film to a discrete film. Did y'all see any appreciable weight savings just from the idealization change?
I wouldn't say just from the idealization change. I think that was just, I mean, we ended up using it to very quickly study and very quickly kind of down select our laminate families. One kind of related area where we saw big weight savings was that we were approaching our, I mentioned about being a little too highly tuned for first pass yield and for the layup to be, balanced, symmetric everywhere. We kind of, as we had to go back to the drawing board, invoked some experience from our tech fellows, and they said, well, we know you have sandwich panels all over the place, but, you can actually cut loose some of the, we were doing kind of, we'll call them ply packs, that kept everything balanced and symmetric pretty much everywhere. And we had to kind of get a little more aggressive there. So I wouldn't say that that find was not necessarily in the smeared properties. It was just in inspecting how we were doing our layup with the discrete laminates.
one more thing to complete your question about 1-to-1 ratio between stress and design. Once we get to the final design, final sizing phase, and we had our process set up, stress was actually overwhelming design. They couldn't actually receive the sizing from us. So we went back to that, what Craig said yesterday, instead of being a data manager, the stress is nowadays, go back to the old ways that was one stress for 5 people. Yeah, we could have had that ratio because I was delivering sizing and my design lead said, I don't have anybody to give. So actually design was holding us. That's why you saw that curve that all of a sudden we just, whoop, we went up. But it took us some time to get to that. Once we set up with the Bell methods, we just hit it.
I know if we had a designer with us, they would rebuttal, but that's okay.
Hi, great presentation. So one of my questions is, you were talking about the sizing and static sizing, but being a rocket ship, the dynamics, the tail design, flutter, did you guys consider any dynamics, using HyperX to consider any of the dynamic effects?
Yeah, so we didn't have any stiffness criterion at sort of the gross level. We tracked stiffness, and that was sort of a deliverable to the VG customer, who was really the Flutter team. So we set up a model that takes section cuts, and we tracked our displacements due to a unit load kind of across the boom and across the feather, and we would output that to VG every time we had a new FEM iteration available. So that's kind of how we were tracking it at the gross level, or I guess I'll call it the acreage level, but we didn't have any stiffness criteria, and it was just a way for them to track it, the direction that it was going. For some of the flight control surface, I'll say fittings or sort of these single load path, highly stiffness critical components in the flight control surfaces, we did have specific criterion that we designed to, but it was really just at the component level, and it was typically in a however many degrees of freedom was critical for that specific joint. They would just give us pounds per inch or an inch pounds per radian target for a specific component.
Hi, for the different phases of the program, did you find yourselves limited by using element forces to do some of the core ramp or joint sizes? Or were you able to find other ways to implement those or ways to model them effectively?
You got involved. Nice. The core ramp was always a major debate on how we're going to do it. At Bell, based on the legacy programs, we're not very concerned about them because of the excess of resin that you have in there. So at some point, the schedule is so aggressive that we're proposing to ignore, and that pretty much based on the lessons learned. But I know that Justin was somehow got direct contact by VG and was developing something, right? At some point, you guys were looking into it?
Yeah, at some point we were, but I think they kind of ended up putting that on hold as well.
Also, by ignore, Max means certain checks.
Yeah.
That historically, we only check at certain other cross-sections that bound the bevel, not right in the bevel. So I'll just say it that way. Certain checks we knew historically, but it did make for an argument point with our customer, right? We had to prove to them why we're comfortable with that.
Thank you guys for your presentation. When you transition from the model representing bonded joints to having the explicitly defined fasteners, how did you determine what your fastener patterns actually look like? Is there a plugin that you guys use to determine, this fitting needs 4 versus 6? Or did you use more traditional methods for that?
I'd say that's where a lot of engineering judgment came in. Early on, early load levels, getting fastener count and size. We just kind of gave it a first pass and then just started dialing it in as we started sizing. So we leveraged just experience there, and we're lucky to have a really good group that could kind of get us in the right ballpark and then go from there.
Yeah, within HyperX, you have the capability to either choose discrete or just have your running load and define how many fasteners you want for that joint based on the boundary between zones.
This is the edge joint capability.
Yeah, that's the edge joint,
So
and we are playing with that
loads.
to give us an idea.
Okay, thank you.
George, I have a question for you about the part-by-part weight targets. Is that something that was like a program requirement from historical data, or did you analyze that in HyperX?
So the first part of that is, was it a program requirement from how Bell approaches it, or?
Just how did you get your part-by-part weight targets?
Yeah, okay. So we had gone through a preliminary phase, so we had sort of ballparks of where we used to be. That created the upper bound, right? Then we had those weight studies, and we had a way to map the weight studies to which parts are affected by which ones. So that was definitely helpful in setting our minimum bound. And then we have weights engineers that did their weights magic, and found the balance between those two bounds, kind of spread it evenly, peanut butter spread. Weights is not a perfect science, but knowing where we are now and how we were able to work our way out, it was a decent approach. We found the right balance of dialing in bounds and then ultimately targets for every for every part.
Thank you.
So from the beginning, you talked about the environment that this operates in, from like a negative 115 degrees to 350. So having worked composite structure that's a mixed match with metallic substructures, did you find thermal loading or thermal environments was a significant driver in your design? And how did HyperX take it? Did you just use it as a single load condition or ignore it altogether?
No, that was definitely within our loads. The force fight was there in our models. So thermal affected us as it should in probably a lot of programs in 2 ways, right? Depending on the levels, the temperatures. But we took material knockdowns, which HyperX was key to be able to quickly do that, and assigned the correct material knockdowns for the given load case combination. But also obviously the force fight from dissimilar materials, that's just picked up by the way we modeled. And also it kind of goes with what Justin was saying about how we have scripting to automate our fastener creation in our FEM. So we have every fastener discretely modeled with the right stiffnesses for the size, diameter, type, so we trusted that those loads were showing up and being sized for.